This session will be shown some numericals on equivalent circuit diagram of a transformer from open circuit and short circuit test data. How to draw the equivalent circuit diagram from OC and AC test. The first numerical I'll take up for the regulation of the transformer. A 20 kVA 2500 or 500 volt single phase transformer having resistance of 8 ohm and zero point 0.3 ohm in primary and secondary respectively, and similarly 17 ohm and 0.7 ohm respectively for reactances of the primary and secondary. Find the voltage regulation and the secondary terminal voltage for power factor of 0.8 lagging and 0.8 leading. The primary voltage is held at 2500 volts. For this particular condition, it is a loading condition, you have to find out what is the terminal voltage V2 across the load, and also you have to find out what is the voltage regulation of the transformer. First you have to list out the data, then our intention is to find out the drops in the resistance and reactances. Then knowing the values of the rating of the transformer, then how to determine the value of feed. Just you have to proceed with the transformation ratio. First, from the given data of 2500 or 500 volts, find out what is the transformation ratio. That is nothing but E2 by E1 or V2 by V1, that is equal to 0.2. Then we are interested in a full load current of the primary and secondary. Also, we know that the applied voltage is V1 is 2500 volts. Then the secondary voltage on no load, you have to make it a point here. Secondary voltage on no load, that is E2. E2 is equal to K times E1. That is no load voltage, and the under no load condition voltage remains 2500 by 500 volts. That is nothing but it is written E2 is equal to K times C1, that is K times V1, because under no load condition the V1 is equal to E1, therefore E2 is equal to K times C1, that is what we are getting is 500 volts. If you know the value of the induced voltage in the secondary as a 500 volts, then if you know the loading factors and also the value of R2 and X2, then it is possible for us to calculate what is the V2. That is, we know the E2. To find out V2, then what you have to do? In the E2 you have to deduct I2 RO2 cos phi factorially, I2 XO2 sin phi factorially, or you have derived the equation for voltage drop in the transformer. That is nothing but I2 R2 cos phi plus I2 X2 cos phi is the voltage drop in the transformer, and it is a lagging load. I2 R2 cos phi minus I2 X2 sin phi for the leading power factor. Okay. Then equivalent resistance as referred to the secondary side. I am calculating equivalent resistance as referred to the secondary side. Then RO2, that is the total equivalent resistance of the transformer referred to the secondary side, is the resistance of the secondary itself R2 and K square times R1. Therefore, you can calculate the value of RO2, that is 0.62 ohm. Then similarly calculate the reactance, that is XO2 is equal to K square X1 plus X2, that is 1.38 ohm. Then full load secondary current, we know that is 20 kVA into 10 raised to 3 divided by 500, that gives the full load current of the secondary, that is works out to be 40 amperes. That is 20 into 10 raised to 3 divided by 500, that is 40 amperes. Then where E is given the power factor, first we consider lagging power factor. Then sin phi also we are calculating, that is if the cos phi is 0.8, sin phi corresponding sin phi is 0.6. Then voltage drop in the transformer winding at full load and 0.8 power factor lag, that is we already derived this equation, that is I2 RO2 cos phi plus I2 XO2 sin phi is the voltage drop in the transformer. Therefore, that is equal to 40 into 0.62 into 0.8, because I2 we know the 40, RO2 we are calculated, cos phi 0.8 is given. Similarly, sin phi is also known, XO2 is also known, and I2 is known. Then the total voltage drop in the transformer is 52.96 volts. Then secondary terminal voltage, that is V2, is equal to E2 minus voltage drop. That is how we are getting E2. E2 we are getting, V2 how we are getting, we are deducting the voltage drop in E2. So that is E2 is 500, then the voltage drop is 52.96, then what we are getting, the voltage across the secondary of the transformer terminals is 447.04 volts. Then the voltage regulation is nothing but the voltage divided by the no load voltage, that is I2 RO2 cos phi plus I2 XO2 sin phi divided by E2 into 100. This is E2 into 100. That is 52.96 the voltage of 500 is the no load voltage, multiplied by 100, that we are expressing in terms of percentage regulations, that is 10.592% is the regulation we are getting. Then we have to calculate for leading power factor also, voltage drop in the transformer winding at full load 0.8 power factor leading. In the leading case, this sign is becomes minus, that is I2 RO2 cos phi minus I2 XO2 sin phi. That is what we are getting here is this voltage drop. Then if you are working out, then you are getting the voltage drop is minus 13.28 volts. You have to observe here, it is a minus 13.28. I will comment on this one. Then secondary voltage, once again the same formula, that is P2 is equal to E2 minus voltage drop. Here voltage drop is minus, this minus of minus is plus. Therefore, it is 500 minus of minus 13.28, then what we are getting is 513.28 volts. What we are observing here is, when there is a power factor is a leading, it is giving the reactive power, so that is the voltage, what is the available voltage across the load is greater than the generated voltage, because it is giving out the reactive power. That is why the voltage across the load, when it is a leading power factor, the terminal voltage is greater than the induced voltage. Therefore, we are getting negative regulation. That is why you are getting a negative regulation when if you are calculating the regulation at lagging power factor. Therefore, what I am doing here is voltage regulation is minus 13.28 is a voltage drop divided by 500 ohms. That is a voltage regulation for leading power factor. What I am getting is minus 2.656%. This is how you have to calculate the percentage regulation of the transformer. Then the next numerical that are on the equivalent circuit diagram of a transformer. Here you have to draw the equivalent circuit diagram of a transformer from the data of open circuit test and the short circuit test. Here the open circuit test is performed on the LV side of the transformer, and short circuit test is performed on the HV side. That is quite evident. Then the data what is given is 250, 1.4 amperes, 105 watts under the load condition. That is open circuit test. For short circuit test, 120 volts applied voltage, the corresponding rated current is 8 amperes, and the power consumed under short circuit test is 320 watts. He asks you to draw the equivalent circuit diagram for refer to the low voltage side and the high voltage side. We will look into one by one. First, from the open circuit test data, our objective is to find out R0 and X0. And from the short circuit test, our objective is to find out R equivalent and X equivalent. Okay, these are the two objectives. Based on the given data, first you have to find out that particular site, the value of R naught, X naught, R equivalent and X equivalent. First, from the OC test, it is conducted on a LV site that I am considering as a primary site. HV site I am considering as a high voltage site. Therefore, cos phi naught, what I am getting here is cos phi naught is no load voltage power divided by primary voltage multiplied by the, that is in the denominator, no load current. From that I am calculating the value of the cos phi naught, that is what I am getting here is 0.3. Then the energy component of no load current, that is our you are interested in finding out R naught and X naught. To find out R naught is equal to, that is the applied voltage, that is the primary voltage divided by IW. X naught how we are calculating, it is the applied voltage divided by the magnetizing component of a current. Therefore, first I am calculating energy component and the magnetizing component of the transformer. That is IW, I am getting I naught cos phi naught, that worked out to be 0.42. Similarly, I am calculating magnetizing component, that is I mu, what I am getting here is 1.3355 amperes. These are the working component and the magnetizing component of the no load current. From these two data and the applied voltage of 250 volts, then what I am calculating is R naught and X naught. That is, you are conducting on LV side, that is I am treating as a primary side because 250 is the primary side what I am considering. Therefore, refer to the LV side, the value of R naught is V1 divided by IW, and that is equal to 595.2 ohm, and no load reactance X naught, that is parallel combination resistance and reactance V1 divided by IM, what I am getting is 187.2 ohm. These are the R naught and X naught, what I am getting is from the LV side. That is what I am considering this as it is a primary side. Then the SC is, that is it is conducted on short circuit on the HV side, means the meters are connected to the HV side, means it is connected in the secondary side, what I am calling. Therefore, from this data, what resistance and reactance, equivalent resistance and reactance what we are getting is referred to the secondary. It is referred to the secondary because it is conducted on HV side. The HV side here we are treated as the secondary. Therefore, we are getting RO2 and XO2. Therefore, the short circuit current, that is what I am getting here is 8 amperes. 8 amperes. Okay, and the voltage applied under short circuit condition is 120 volts. The power consumed is 320 volts. I am using these three data to calculate R equivalent and X equivalent refer to the secondary side. Therefore, that is the power is 320. These are the three data what I am using. Then equivalent impedance we are getting from this data. How we are getting the impedance from resistance? Sorry, the voltage and the current. It is V by I gives the impedance. Therefore, equivalent impedance it is referred to the HV side because we are connecting all the meters in the HV side. Therefore, I am considering as HV side. The HV side is nothing but secondary side. Therefore, I am representing this as ZO2. That is VSC by ISC. The corresponding the value of the voltage and current under short circuit test are 120 and 8. Therefore, 120 divided by 8. What I am getting here is 15 ohm. Similarly, the equivalent resistance referred to the HV side. How we are finding out the resistance? The resistance is consuming the power in the transformer. That is I2 I square R is equal to the power consumed. The power consumed is 320. The current is 8. Then the corresponding value of the resistance can be calculated. That is nothing but RO2 is equal to, that is short circuit power divided by ISC square, or the short circuit power P is corresponds to ISC square in RO2. ISC square into RO2 is nothing but the power consumed. In turn, RO2 is PSC divided by ISC square. So that what I am getting is the 5 ohm is the RO2 what I am getting. The equivalent reactance refer to the reactance refer to the HV side, second side. RO2 is known, ZO2 is known. You can calculate XO2 and that is equal to underscore ZO2 square minus RO2 square. Therefore, what I am getting is 14.14 ohm is the resistance. What I am reactance refer to the second side. What I am getting. The transformation ratio of the transformer as 2500 divided by 250, that is 10. Therefore, you have to draw the equivalent circuit diagram, refer to the secondary side as well as the primary side. First, I will take up the primary side. We know R0 and X0 refer to the primary side. That is, this is our LV side. LV side means it is the primary side because OC is conducted on LV side. Now I want to draw the equivalent circuit diagram on the LV side. But however, SC side we are conducted a SC test. Resistance and reactance what we are getting is refer to the secondary side that I am to transfer to the primary side. Okay, that I am doing here. Therefore, equivalent resistance refer to the LV side, primary side. These are the secondary side, primary side. What you have to do? You have to divide by square of the transformation ratio. What I am getting is 0.05 is R1 and X1 is 0.141 ohm. If you know all these R01, X01 as well as R0 and X0, you can draw the equivalent circuit diagram, that is refer to the primary side. R1, X1, R2 by K square, X2 by K square, then this R0 and X0. Then further if you are reducing, what I am getting here is, okay, see here, it is referred to the primary side. It is referred to sign, therefore it is R01, X01, R0 and X0. This you have to draw the equivalent circuit diagram refer to the second primary side. Then the one more task it is given to the as an exercise. We know the value of RO2. We know the value of RO2. We have already calculated RO2 and XO2. It is already there, RO2 and XO2. Means equivalent resistance refer to the secondary side, equivalent reactance refer to the secondary side. The only thing is that you have to transfer this R0, X0 to the secondary side, because R0 and X0 were calculated on LV side, that you have to convert into the secondary side by multiplying K square times R0 and K square times X0, and you have to redraw the this equivalent circuit diagram refer to the primary side. Here you have to draw the refer to the secondary side. In that case, this should be replaced by RO2, this should be replaced by XO2, and this is replaced by K square times this value and K square times this value. Okay. Similarly, here what I am getting is V2 instead of V2 by K, and what I am getting is V2, and what I am getting here is it is K times V1, and here what I am getting is the I1 dash, that is I2, and it is K times I1. What I am, sorry, I1 by I2, that is I2 is equal to what I am getting is the value of the current which is referred to the secondary side. This is how you have to draw the equivalent circuit diagram referred to the primary and secondary side by the data given by the OC and SC test.